We've got a quick lesson today on the reversibility of Bronsted-Lowry reactions and conjugate acid-base pairs. So we're going to use one of the reactions that we looked at yesterday in introducing the Bronsted-Lowry theory, a really important one between ammonia, NH3, and water, H2O. And again, here are the reacting materials shown here. And we saw what happened in the reaction the other day is that a hydrogen breaks off. Remember, as soon as it breaks off, it turns into an H plus because it left its electron behind, and it joins the ammonia to make the ammonium ion. So one of our products is ammonium. And of course, the water here has turned into hydroxide because it's lost the hydrogen, but it has that extra negative charge from the electron left behind by the hydrogen. So hydroxide is one of the products. And remember, that makes ammonia an Arrhenius base because it provides hydroxide in solution. Ammonia is also a Bronsted-Lowry base because it received a proton from water. Okay? And remember, in the Bronsted-Lowry theory, if we put, let me put the hydrogen back here, the proton passer, so again, as soon as it leaves, it's a proton. So we look at the proton being passed from here to here. The passer is water, that makes it the acid, and the receiver is ammonia, which makes it the base. And we can kind of diagram that on the reaction itself. This is not a normal part of the reaction, but this shows that for the reaction to occur, water is passing ammonia a proton. Right. The idea of reversibility says that many chemical reactions can be reversed, and this is certainly one of the most important examples. So if ammonium, because it's ammonium now, were to pass the proton back to water, once it got there, it would find its old electron and turn back into a hydrogen. So that's exactly the reverse reaction. And you'll notice that this reverse reaction starts with ammonium and hydroxide, but it ends with water and ammonia. So we can just show the reverse reaction by drawing an arrow from right to left. We turn the ammonium and the hydroxide back into ammonia and water. Okay? What's very important, though, about this reverse reaction, if we play it again, ammonium is clearly giving up a proton. Again, here's the proton being passed over here. And whatever passes the proton is an acid. So ammonium is some form of an acid. Right? And then hydroxide gains that hydrogen. Okay, it turns into water here. So hydroxide is a base. Okay, so not only does hydroxide signal that a chemical has created it is a base, but hydroxide itself is a base. All right? So in the Bronsted-Lowry theory, both the forward reaction and the reverse reaction have an acid and a base. All right? Moreover, okay, two of these things are related to each other. All right? If we wanted to diagram the reverse reaction, we would show the proton going from ammonium to hydroxide. So again, if this were still hydroxide, the H plus would go over here, the charges would cancel out, and that's passing a proton from ammonium to hydroxide. Right? What you'll notice is before and after the reaction, certain things look similar. Like ammonia does not look that different from ammonium. Okay? The only difference is a hydrogen and a positive charge, and you can clearly see without it, with it. Okay? So here, ammonia and ammonium are called conjugates. Okay? More specifically, you would call them a conjugate acid-base pair. Okay? They're very much alike, except they differ only by that hydrogen. Okay? Likewise, water and hydroxide are also very similar. That's what water looks like. And then hydroxide looks like that without the hydrogen. So again, it's missing a hydrogen and it's got a lower charge. So water and hydroxide are also conjugates. And every one of these Bronsted-Lowry reactions has two conjugate base pairs. And you'll notice that on one side, the ammonia species, okay, is a base. On the other side, it's an acid. That's why I called it a conjugate acid-base pairs. Okay. On the left side here, water is an acid, but its conjugate hydroxide is a base. And that makes sense because once something has given away a hydrogen, like hydroxide has, it's capable of taking it back. And giving away is acidic property, taking it back is basic property. And same thing over here with ammonia. Ammonia is usually a proton acceptor. Oops, I'll make it a proton here, making ammonia a base. But now that it has an extra proton, it could give it away, making ammonium an acid. So that's the idea of conjugate acid-base pairs. We're going to learn actually more about this and more about this equilibrium after we learn about the strengths of acids and bases. So that's it for today. You'll be finishing up your POGL, and we'll talk about that really interesting stuff about strength and equilibrium next week sometime. All right, have a good one. Have a great weekend.